All right, everyone, we're going to go ahead and get started. Thank you so much for being here. My name is Cinnamon Moffat. I am the associate. We have phones making noise. There we go. So I'm going to be your host for this evening, and I'm so glad that you are here. This is a hybrid event, so if this is an event you haven't joined us with, we have folks online and folks in the room. For folks online, this is a webinar, so that means your cameras, mics, and screen shares have been disabled, but we have a volunteer in the room. Hi, Roseanne. Uh, she will help with any technical questions you might have or any questions for today's speaker. All you need to do is type them into the chat and she'll read them out and address those. So please engage with us using that chat box. For folks in the room, in order for the folks online to hear you when you have questions, just raise your hand and I'll bring you a mic and you can ask those questions. And that way everybody, whether they're here in Newport or somewhere else, they're able to engage with us. But again, I just wanted to thank you so much for being here at our Science on Tap. I got a couple quick announcements and I'm going to hand off this intro to somebody else. I wanted to just let everybody know that Marine Science Day is coming. Yay! So if you don't know about Marine Science Day, it is the day that we open up behind the scenes here at Hatfield, and you're welcome to explore all over the place. We'll have around 40 to 50 exhibitors, and it's kind of like a kids' science fair, but you get to go learn about all the different types of research that happens here. So this is on the 12th of April. It's a free event. It is from 10 to 4, and it's a really fun day, and I hope that you can come and join us. So Marine Science Day is right around the corner. And then next month, we'll have another Science on Tap. We have our Laverne Weber visiting scientist who will be here. Her name is Marley Parker. She's a freelance videographer and science communicator that talks to us about what it's like to go out to sea and document. And right now, communicating science is really important. So I'm really excited to have Marley come and join us. So those are two upcoming events. If you are curious about any of our events, and you would like to learn a little bit more, you can sign up for our email list just for public events. That's down here. If you already get those, you don't need to sign up. But if you would like that, it's only for these kind of public events. Or you can go to the HMSC website, go to the events page, and scroll around on there, and you'll find all the information about upcoming events and how to participate online if you can't come here in person. I'm really excited for today's talk, but I'm going to hand this mic off to our AVP, Bob Cowan, who's going to introduce today's speaker. So go ahead.
Thanks, Cinnamon. I'm really happy today to be able to introduce our speaker, Dr. Tuba Özkan-Haller. She's the Dean of the College of Earth and Ocean Atmospheric Science and also professor in that college. So she spent most of her career at the intersection of physical oceanography, marine geology, and coastal and ocean engineering. And she brings a really interesting perspective to coastal processes in that context. Her research focuses on a combination of skill sets. She uses numerical field, laboratory, and analytical approaches to arrive at predicting and understanding ocean waves. And so having relevance to something that affects all of us or potentially affects us of the sneaker wave, this is perfect. In pursuing her work, Tuba has been the recipient of a variety of honors, and I'm impressed when I look at the list, but she's been recipient of the Office of Naval Research Young Investigator Award, the Outstanding Faculty Member Award at the University of Michigan when she was there, and the Patullo Award of Excellence in Teaching at Oregon State University. So she's hitting a lot of really important recognition. She currently serves on 2 federal advisory committees, the Board of Coastal Engineering and Research and Hydrographic Survey Review Panel. I think particularly relevant is that she's been very extensively engaged in the National Academy of Science, Engineering, and Medicine. And she's served 2 terms on NASA's Ocean Studies Board. And that's for those within the marine studies, that's a really critical board. And she served as member of the Marine and Hydrokinetic Energy Assessment Committee. She received her BS in civil engineering from Bogazi University. Don't know if I said that right.
Close enough.
In Turkey, and a master's and PhD in civil engineering from the University of Delaware. So please join me in welcoming Tuba.
Thank
Thank you, Tuba.
Thank you. Thank you all for being here tonight, here in person. It's great to see so many of you, and also those of you who are online. I really appreciate that you're here. Today we're going to be talking about waves, and waves is something that I have just been passionate about all my life. I'm the daughter of a Navy officer. We always moved around a lot, but we were always near a beach somewhere where you could look out and see these beautiful waves roll in. And so I'll start with that beauty idea first, right? Ocean waves are really beautiful. And God, I could just like have slide after slide of waves of how intricate and complicated and gorgeous ocean waves really are. They also form beautiful beaches, and certainly the Pacific Northwest, Oregon, we've got plenty of those, right? Beautiful beaches here. And really, waves are responsible for the fact that the sand stays on the coast, right? That it isn't just all going into the deep water. Waves are what is responsible for the fact that we have beaches at all. And of course, waves are a lot of fun, right? We like to play in waves, play in beaches, lots of fun to be had there. But from a practical perspective, they also carry a lot of energy. And this energy is really, ultimately it starts with the sun, right? Solar energy gets converted into wind energy, and it is winds that drive waves. And along every one of those steps, the energy actually becomes denser, if you measure it in terms of the amount of energy per square foot, for example. So perhaps it's not so surprising, waves carry a lot of dense energy, and they are the envy of wave energy conversion companies who are interested in figuring out ways to harness that energy and as a renewable resource. And of course, you all are aware that OSU is building the US's first grid-connected wave energy testing facility in a way that is collaborative with the communities here. So we're pretty proud of that work. Construction's really about to end here, so we might have our first wave energy testing situation coming up here any day now. Okay, waves also inspire creativity. If you just Google waves and art, and you're going to get all kinds of ways in which humans have really engaged with creative work that involves waves. At the bottom right here, Bob mentioned I was for 3 years a faculty member at the University of Michigan. And at the bottom right, this grassy field that you're seeing is an earth sculpture by Maya Lin at the University of Michigan that portrays a certain very special kind of wave field. And it's giant. You can, walk in it, and kids do. Really hard to mow though, so. But speak about creativity. So waves also, I think, inspire people. There's a sense of awe when you're watching waves roll in, when you're listening to them. There's a sound. I certainly have been inspired by waves all my life. And one of the reasons I moved to Oregon is because of the waves here. Gosh, the waves here are majestic. I had never seen anything like that when I moved here. In fact, the folks who were recruiting me, picked me up at the Eugene airport, and Rob Holman and his wife, Kathy, some of you know them, and drove me out to the coast. And I was just in awe. It was an April afternoon. The sun was going down. The waves were giant, spray in the air. And, it looked like thousands of rainbows in the air. I was just absolutely just in love. Now, why is it that waves here are so majestic? I call them. They actually get bigger than waves really most anywhere else on the planet. And you all know this. Most of you, I'm sure, live on the coast. But waves here reach the 10-meter height range, so 30-foot waves, at least once a year. And they reach the 15 feet meter height, so 45 feet. So that's a 3-story building, right? And that happens at times, right? Certainly have been recorded. And waves here almost never get smaller than 3 to 6 feet. And compare that to the East Coast, where I did my graduate work. waves of 3 to 6 feet, 1 to 2 meters would be considered large there, right? So really quite something. Okay, waves also fuel strong currents. I'm going to zoom into, for example, this particular feature here seen from above. This is what a rip current would look like if you were to fly over this stretch of beach. Rip currents can be very destructive to property because they basically can take a lot of sediment offshore as they're traveling out. And that can result in things like this, where the sediment is essentially scoured away from under homes, even in homes that were positioned relatively high. These currents can move a lot of sand around. Here on your left-hand side, you're seeing images taken from the exact same location of a beach in the summer and the winter. And you see the rich sand cover in the summer that is not present in the winter because the currents driven by these strong waves pull the sediment off the beach, but then the waves later, the calmer waves of the summer, will bring that sediment back. So really powerful currents that can move a lot of weight around. Really powerful currents that can move a lot of weight around are also a hazard to beachgoers. And rip currents are one of the leading causes of ocean-related fatalities. This, of course, rip currents mostly affect people who were already planning to go in the water, right? You're in the water, you get pulled offshore by a rip current. And I just want to spend just a minute talking about what to do if that was to happen. And this is very standard advice, right? Don't panic, don't swim towards shore because these currents are strong enough. I once calculated out that even Michael Phelps could not swim to shore against these currents. That's how strong they are. I'm no Michael Phelps, so what I'm going to do is I'm going to swim parallel to shore to get out from the influence of the current. They're usually relatively narrow, as you could see from the aerial picture that I was showing earlier. But when you're in the current, it is hard to see where the current starts and ends, right? So swim parallel to shore or calmly float because the circulation pattern is such that eventually you will come back to shore because of the way the circulation pattern closes. Of course, rip currents aren't so big of an issue here in Oregon, where not very many people willingly go in the water. But they are a much bigger issue on the East Coast in Florida, for example. And it's interesting when you look at the literature of the incidents associated with rip current injuries or fatalities. And the statistics are really surprising. A lot more people, a lot more men are pulled offshore by rip currents. Usually it's tourists who don't know the beach very well. And oftentimes what the researchers have found is that people who are impacted by rip currents are those who think they are really, really strong swimmers, so overconfident in their abilities. And I mentioned this because I myself have a very healthy respect for the ocean. And I think having a healthy respect for the ocean will serve us well. And so just a note of caution there. That brings me to the topic of the day. These waves, so beautiful, can also be a very significant hazard. And today I'm going to talk to you about some of the incidences that have occurred off of the Oregon and Washington coast. Some of these stories are pretty sad, but I want to share them with you because I think it's important for us to understand better how these waves form and how we as individuals can make decisions that can hopefully keep us out of harm. And so hopefully, I'm hoping you will walk away from today's talk with some very practical tools about how you can keep yourself, your family, your loved ones safe. So let's first start with some definitions. So sneaker waves really are essentially, keeping my eye on the time, are essentially very unusually large run-up events. So you go to the beach, oftentimes before you decide where to put down your blanket, you might watch the beach for a few minutes. Most people don't watch the beach more than 5. And at that point, you make your decision, and maybe you pick a spot that looks pretty dry to put your blanket down or hang out around. Now, these are unusually large run-up events that essentially will catch you by surprise. You have no idea that the water could come that far in. As far as the hazard is concerned, these waves usually affect individuals who were not planning to go in the water, right? So oftentimes it's December or January, but it's a beautiful sunny day, no wind. We make it out to the beach, but we're wearing boots and a jacket and heavy clothes and jeans. And so once a person gets pulled into the water, all of that weight really makes it even more difficult for them to escape. So, and this is in contrast to rip currents, right, that affect people who were planning to go in the water. So it was really about 10 years ago when we received a grant from the National Science Foundation to study this phenomenon. And I mention that because the National Science Foundation primarily funds basic research, and that's exactly what this is, basic research. But I will also tell you the ways in which we can carry out this basic research that has impact immediately on the lives of individuals who live on the coast. In this particular case, we proposed to do this work in collaboration with the National Weather Service. So the Portland, the Medford offices in Oregon, as well as the Eureka office in Northern California were close collaborators. And some of this work that I will tell you about, both led by students, were co-authored by those individuals. And that's one way to make sure that the knowledge that we create immediately is transitioned into the forecasting tools that people use in their everyday lives. So this first work I'll tell you about was led by my student, Gabriel Garcia Medina. And he essentially got his hands on Coast Guard records that detailed incidents that were bound to sneaker wave issues that caused injury or death, 25 such events over the course of 12 years. And so you'll say to yourself, well, so okay, 25 over the course of 12 years, so that's about 2 a year. Right? And it's true. It's about 2 incidences, major injuries or fatalities that required the Coast Guard to get involved. And that might not seem like a big number, but it's 2 years, 2 people, year after year after year after year after year, right? So I call this a slow bleed. It's not a big event that kills a lot of people and gets a lot of press, but over the course of 50 years, it's actually a lot more people that get impacted by sneaker waves than get impacted, say, by hurricanes. So what Gabriel did is he basically looked at these incidents that were recorded by the Coast Guard, and he really dug deep. He did some forensics to try and figure out what the circumstances were that were associated with these waves, and if there was a pattern that we could find. So I will tell you about 4 of these events that he detailed, and this is where the stories get a little sad, so hang in there with me. This particular event took place right here off the Newport jetties. People like to walk out onto the jetties, and this was one of those instances where a couple was observed to walk out on the South Jetty. Now here, I'm showing a couple of plots here, and I want to just walk you through what these are so you can sort of follow along as I tell you about the events. The top panel there on the right-hand side shows, in the darker color, shows what the wave height was during this period of time. And you see that we're going about a 10-hour time frame here. So the wave height was hovering right around 4 or 5 meters for Oregon. That's not big waves. The lighter color here tells you what the period of the waves were. So that's the time period between successive crests, right? So that period was hovering right around 11, 12 seconds. That's pretty normal stuff for Oregon, nothing fancy. The middle image, the blue line in the middle image shows you what the tide looked like on this particular day. So you see that we're about going through kind of a 12 hours, right? So a tide and a half. And then the darker lines tell you what the total water level looked like, and this takes into account things like wind-induced surge and wave-induced surge and things of that sort. And these are all calculated with pretty standard formulas that coastal engineers and nearshore oceanographers have had access to. The bottom plot here shows the probability of overtopping. And this is a quantity that coastal engineers use to design structures. You want to allow for a certain amount of overtopping. So that what that means is that a breaking wave actually goes over the jetty, okay? And in yellow, we have marked the period of time when the couple started their walk out on the South Jetty towards its tip. And you can see that when they started their walk, the probability of overtopping was about 2%. So that means 2 of every 100 waves was overtopping. That's not much. What that means is the jetty was probably looked dry, okay? Well, how long did it take the couple? Maybe it took them 15, 20 minutes to keep walking out. And that's what that yellow area marks. By the time they got to the tip, the probability of overtopping was almost 10%. So 1 of every 10th wave was overtopping. This is a situation, and we found examples of this in the Coast Guard data. I wouldn't call this a sneaker wave. This is an occasion where the rising tides and the increasing wave heights make it such that there's a very abrupt change in the probability of overtopping over the course of 20 minutes, right? And standard formulas would predict this. So I'm hoping that in situations like this that involve structures, that we can actually put in place a prediction methodology that would say during the hours of 1 and 3 on this day, don't walk out. And this is something that we're actively working on right now. Another event that involved what I'm going to call a structure, that this is a natural structure. So on the left-hand side here, you're seeing the topography, the underwater topography. The dark colors are very deep. The really light area is the actual land. And where the pink arrow is pointing to is sort of a rock bridge. And my graduate student actually got obsessed enough with this case that he drove out there on a weekend, dragging his wife along, who didn't know what they were doing, what they were about to do. And he went and stood on this rock ledge and measured its elevation and, really dedicated to really figuring out what happened. This was the site of 2 fatalities. 2 young men, high school students from Eugene, had gone out to Yachats with their friends to celebrate and decided to stand on this rocky ledge bridge to take a picture, and were caught off guard by the wave and perished. And there was a OPB documentary that was made about this particular case, interviews with the mom. That was really impactful to me, and that was around the time we were writing our proposal to the National Science Foundation. Here too, the story is not dissimilar from the story I just told you about the jetty, where essentially the probability of overtopping rapidly increased. So even though the rock bridge might have looked dry when the boys went there, soon enough, after hanging out there for a short amount of time, 16% chance of overtopping, so really high chances. This is another story, Nescoin Proposal Rock. You see the outline of Proposal Rock there, in white in the middle of the image on the left-hand side. This is another really sad story where a gentleman was getting ready to propose by the Proposal Rock to his girlfriend. And they waited on shore. Here, the one unusual piece about this is, compared to the other examples, is that the tide was dropping. And in fact, interviews with the gentleman who did survive the event, it was such that they were waiting. He really wanted to propose by Proposal Rock, so they were waiting for the tide to go down and for the waves to no longer lap up. But by the time they went up there, you see that in this case now, there is no structure involved, so we're not looking at overtopping probabilities. Instead, we're looking at run-up probabilities. I've got plotted there on the lowermost panel of the figure, tells us that there was about 2 waves per hour, 2 run-ups per hour that would reach the back of Proposal Rock. So that's 1 every 30 minutes. So the timing of the couple walking out to the Proposal Rock was really unfortunate. Fourth story. This story was actually one that was very difficult to explain. So let's look at these figures and what the data are telling us. So the wave height during this particular case, so this is Charleston, so entrance to Coos Bay. What's pictured there on the left-hand side is the South Jetty, and the incident occurred just south of the South Jetty. The wave heights are, again, not so big, 3 to 6 meters of wave height. That's not unusual for the Oregon coast. The periods are long, 20, 24 seconds. That's really long swell coming in, so that's an interesting clue. The yellow area again marks the timing of the incident that was reported by the Coast Guard, and you see that it is during rising tide that's happening, and that's quite common. And then the bottom line tells you about the probability of overtopping. Less than 1 wave per hour is overtopping. So, is it kind of like folks tended to be there at the wrong time? We wanted to dig into this case a little bit more. It felt like it was difficult to explain with existing knowledge why this particular case happened. And this is when we stumbled upon a video, a YouTube video that was taken at this location at that exact time. And I'm going to show you what that video looks like. And what the video is taken by somebody who is essentially standing just to the south of the South Jetty. And this image here is showing you their view of the South Jetty, right? Of the South Jetty from the south, okay? So beyond those rocks is the actual inlet. Does that make sense? Okay, here it goes.
Another rather large wave coming at me here. Let's see if it's going to find. Folks down playing on the beach here. Uh-oh, I have time to go here. Get out of the way! Go! Whoa, that was scary. That's a big snooker wave. My God, that's huge. I just got out of the way. Would have taken anybody in its path. Look at that. Holy, you know what?
So this is essentially water that's now flowing into that area between the grassy land you're seeing to the south of the South Jetty and the South Jetty itself, right? It's flowing. My graduate student got in touch with this individual, with this gentleman, and interviewed him. And he said that this was the second wave, that 5 minutes earlier, there was an occurrence just like this. And that's why he pulled out his camera and stood ready to see if it would happen again. And as he's narrating, you can sort of hear that anticipation. Okay, that was a kind of a large wave, right? And then, oh, there it comes. That was really intriguing to us because our models predicted that it should only be 1 wave an hour that should be able to reach this height. But he was talking about a sequence of waves that were arriving every 5 minutes. We really dug into this case. And we found that during this period of time, there was multiple videos that were posted on YouTube that pertained to people running out of the way of a sneaker wave up and down the coast. I guess I tend to have graduate students who get obsessed with these things. At this point now, Gabrielle has graduated, and it is my next graduate student, Tron Lee, who's working on this. And he really dug in and tried to understand what these videos were telling us. So in that sense, it became kind of this crowdsourcing type study or approach. So I'll show you another couple of videos here. And this one is from an incident in Washington, same day, by the way, within the course of 4 hours, all of this is happening up and down the coast. And the first video I'll show you, there's this little inlet here. First video I show you was filmed on the south side of this little river. And the view that you're looking at is looking outward towards the ocean, and you sort of see both on the right and left sides of the image the land, right? So that's really the inlet. Water just keeps on coming. It just keeps on. It doesn't even look like a wave, right? It almost looks like a mini tsunami. It just keeps on coming. But then it does turn back around and the water recedes again. And in fact, when somebody is caught in a sneak wave, that's the most dangerous part because they get swept offshore in really, really deep water. In the unrush phase, the wave just keeps on. The second video I'll show you is taken just across the river. So in the first video, you could see in the middle there, so I don't know how clearly you can see that, but there's some pilings that are sticking out of the water. So you're going to see those same pilings from the other direction here in this particular video. Look at those giant logs, right? Like lots of water. They can carry those logs, no problem. There's actually a third video from this particular spot, a little bit further south on the beach. And this shows what it looks like when you are on the beach and you are sort of backed with a relatively high structure or dune in the back. It is difficult to get out of the way. The individuals ran as far up the beach as they could, and then they ended up somewhere where they would have had to climb, right? And then you see them turn back around towards the waves and just take it, right? And in this particular case, the downrush did not pull them back into the water, but depending on how high the water gets and how wet your clothes get, it could very well happen. So the goal of the study then tilted towards figuring out what was going on this day. You know, we've got the events that where structures are involved and we feel like our existing understanding formulas that we've been using are adequate in explaining them. But this is something different. This is a sneaker wave, right? So we dug into all of the data we could get our hands on. So there is some NOAA provided tide gauges at all of these locations that we dug into. There are NOAA-provided wave buoys that exist off the coast of Oregon. We use that data. And there's also these DART pressure sensors. They're meant to be tsunami warning tools. When a tsunami, far-field tsunami is coming towards us, these buoys, they measure very infrequently under normal circumstances, but if they perceive that there is a significant anomaly, they start measuring more frequently so that the warning can be issued for the Oregon coastline. Okay, I'll start with just the tide data. So here you see 6 panels from the 6 locations up and down the coast. And this looks like what you would expect. The tide is rising and falling and rising and falling, but there's also sort of like this noise in there, you know, something else is happening in addition to the tide. So if we subtract out the tide to just look at what's happening, and this, by the way, the green is the time period where the video that we looked at came from. So if we subtract the tide, now we're looking at sort of the non-tidal residual, the part of the signal that doesn't have anything to do with tides. Tides are very predictable, right? So it's easy to subtract them out. So it looks like something's going on, and something starts right around 1600 hours on January 16th. So we start to think about concentrating on that. And here's the DART buoy data, and this is the data that really intrigued me. What you're looking at here are the DART buoys kind of just like measuring infrequently every other minute. But then something happens, and I marked with the red line sort of that 1600 hours that we just identified, and with the green line, the period of time where the videos were taken. Right after the green period of time, you see that the DART buoy was triggered. that it is now recording at a much higher rate because it thinks something suspicious has happened. Some very large wave has passed over it that it interprets as a potential tsunami. But it is happening hours after the incidents that are captured on video. What's up with that? Okay, and so if this was some sort of tsunami that came in, reflected off, and traveled back offshore, we should also see the incoming signal, but we're not seeing that. We're only seeing something afterwards. So big puzzle. What are the possible causes for this? And you might have noticed that one of the videos was actually labeled a mini tsunami, right? Could this have been related to an earthquake? It's happening all the way up and down the coast. And I'm just going to tell you right away, no, there was absolutely no seismic activity during this period of time. There is a concept called a tsunami. This is something that happens in the Gulf Coast quite a bit. It's related to very fast moving storms that, you know, when low pressure systems move fast, they actually pull up the water surface underneath them because there's low pressure there, the vacuum. And if the storm is traveling just at the right speed that that waveform would want to have traveled at, then it creates a resonant condition. That's like, the analogy here is, you know, like if you have your kid on the swing, it's like you're pushing at the swing at just the right time so that the kid gets higher and higher, right? That can sometimes happen, and then when the storm makes landfall, that wave makes landfall along with it. And there's some evidence of this on the Gulf Coast that this is happening. So we checked this out. And we checked this out by looking at some atmospheric data. So here we are looking at the atmospheric pressure situation data sets from, again, the NOAA stations. Nothing abnormal going on. It's actually a pretty calm day. Wind speed, same thing. Nothing special going on. This is just actually a relatively calm day on the Oregon coast. So immediate tsunami, not it. What else? What else could we be looking at? Okay. We looked at the wave height. We've already looked at this with you. Now I'm just showing you wave height over the course of, how many hours is that? It looks like it's about a day at these 6 sites, 5 sites in this case. Nothing special. These waves are not very big. But you might recall there was kind of a funky thing going on with the period. And when we look here in time, we find that right around the time that we sort of think as the onset of the event, there was a significant shift in the dominant wave period. The day started out with dominant wave periods around 10, 12 seconds. Those are pretty normal Oregon waves. But then there's a very sharp shift to waves that are arriving at 25 seconds, a long swell. This was our first clue as to what was going on. I'm going to just show this. I know there's a few people in the room who are experts in this. This is the way in which we would show graphically the content in the waves at what kinds of periods they're arriving. So on the lower x-axis here, for example, if you look at the lowermost left-hand side, you see that a peak exists there right around 0.05 hertz. So that's about 20 seconds, right? And many of you might actually know about this idea of waves that are arriving at really long periods versus shorter periods, because many of you might have looked at forecasts that are put out by the National Weather Service related to sea conditions and swell conditions, right? The swell conditions, that's the part that's at that very low end of that frequency spectrum, 25 seconds, 0.05 hertz. The sea is the more common locally generated things that are happening. The swell is usually coming from afar. So this here is a time series. So again, we're looking at about a day of what the swell was doing, so the long period stuff, and that's in pink, and then what the sort of locally generated waves were doing, that was in green. Again, I put the line, the red line there is just that 1600 hours we had determined, but it almost exactly coincides with this very sharp increase in swell energy. So then we started looking at, is the swell energy correlated with the elevation changes that we're seeing? And we're seeing some correlation. And why am I looking at this kind of correlation? As Bob said, I have an interest in understanding how the ocean works, but I also have an interest in then bringing that understanding to tools, to predictions, to forecasting. And if we can find a strong correlation, we can use that to forecast. This correlation isn't strong enough. Correlation coefficients at the bottom of about 0.5, not strong enough to really make for a good tool for forecasting purposes. So we had to dig a little bit deeper here. So on January 16th, 2016 taught us that these very large run-up events were observed up and down the coast, that the timing of the initial event aligned with the sharp swell front arriving, and we wondered if we could use that sharp swell front arriving as a litmus test, as a way of finding other cases where this might be the case. And sure enough, I can show you so many more videos. I'm just going to show you a few more. January 18th, 2018, 2 years later, almost exactly the same day, same kind of situation. The tidal gauge data shows us a very sharp sudden increase in tidal in fluctuations, very sharp increase in the pink line, right? That's the swell. Better correlation, still not good enough to really make an index, but here's a video of that day. And this is from a site just north of Oregon in Washington. No fatalities resulted from that particular incident, but you can see how, I don't know how closely you were able to see cars essentially being swept up because of this particular wave. What is causing them? So this is what I'm going to go back a little bit to Waves 101. I'll just take a few minutes here. Most of you, if you're living on the coast, you know that waves arrive in sets. Waves arrive in like 8 or 10 sets. Waves arrive. So every 8th or 10th wave is a large one, and then there's some smaller ones. So if the incident waves are coming in at 25 seconds, right, what happens is these groups of waves then the groups are more like 4 or 5 minutes long, right? Now, as it turns out, when waves arrive in these groups, the water surface underneath the largest wave gets depressed. So there is something that we call a bound long wave that gets generated. The lowermost point of this bound wave is at the location of the highest incident wave. And we call this wave bound because it is really tied to these groups very closely. And is made to travel at the speed of the groups, not at the speed that the wave itself wants to travel. This is a little bit like going back to the analogy of the swing. It's like your kid is, but you're not pushing the swing at the right time. So you're never really picking up steam. These bound waves remain small. And it's not until the whole wave field gets into what we call shallow water that the bound wave is finally moving at the speed that it would naturally move at as a free wave. And that's when it really starts picking up energy. So the fact that these bound waves associated with 25-second waves are about that at that 4-minute mark was intriguing to us, because we now know that in these incidences where the videos were taken, that was the time scale. These waves kept arriving at about 5 minutes, 4 or 5 minutes apart from each other. And so this is when I fast forward through a lot of math, a lot of computer modeling, a lot of digging into existing literature to sort of tell you really the essence of what it is that we found out. We know that the longer the wave is, so the 25-second waves, the deeper the water depth at which they get at this shallow water condition. And that is important, because once the wave reaches that condition, there's a lot of energy that gets pumped into this bound wave that I was just telling you about, that exists at that 4-minute, 5-minute mark. And so 25-second waves enter shallow water in a lot deeper water depth than do 10-second waves, for example. So there's a lot more time for the bound wave to pick up steam and grow bigger. So this results in, so why is it that when we have our usual 10, 12 seconds, we don't see this? Is because there just isn't enough time for the bound long wave to grow. Only when we have this very long 25-second, 22, 25-second swell. And we did a simple model here, and I'm not going to show you the details, but what I am going to tell you is that there is a big difference between waves coming in at 10 seconds and waves coming in at 22, 25 seconds, almost a 2.5 times difference in the amount of energy this bound wave can carry. And those bound waves are exactly what exists at the right time scale. So what are the conditions then that really are, are at play during these times where the last few videos here took place? These are conditions when the incident swell has a very long period. So when you're looking at buoys and forecasts and you see something where the incident waves are greater than 22 seconds, beware. These also happen to be during times when there is not much local seed energy events. So not much locally generated waves, not much chop to kind of confuse the situation, if you will. Now, mind you, a hazard is not just what Mother Nature is doing, it's also what humans are doing to put themselves in the path of the hazard, right? It is during those low wind conditions that people tend to go to the beach, right? It's a beautiful sunny day, gorgeous waves rolling in from afar, it's calm, and so that compounds the situation. So can we assemble a sneaker wave index? And this is something we worked on with the National Weather Service folks. And these graphs, these spectrum is what I've been calling them, really factor into the way in which we can put one together. And I won't give you the details of what this particular sneaker wave index does exactly in terms of the formula and the math involved, but what I will tell you is that this here, what you're looking at is 2 years of data. On the y-axis, on the vertical axis, you're looking at the water surface elevations measured at these tide gauges. So you'll see that mostly they're, the lower half of the graph. There's just a few dots that are on the upper half. Some of them I've marked with green dots and with red dots. Those are over the 2-year period, the 2 dates that I showed you, January 16th, 2016, January 18, 2018. So you see how anomalous the run-up values are for those dates. And on the x-axis is our index. So our index is basically saying that if our index is at 75 or higher, that we should beware, that that's the time we should be signaling a sneaker wave warning. Okay, I want to close with just one more video of an event. This here is in Oregon. That will just give you, again, just a little bit more of a sense of what it feels like to be in one of these. And you see how dry that beach was that he was standing on before this pool. So I want to leave you with just a few thoughts about how you can keep yourself, your family, your loved ones, everybody safe. This first piece of advice, I think, is one that we talk about a lot. Don't turn your back to the water, so be aware, be vigilant, watching. But even when you're watching, especially that last video, it doesn't look like the water is going to come anywhere near that person, right? Just watching the water, it's hard to judge and gauge. So my advice to people is to watch the beach for at least 5 minutes before settling down, if not more. Most people don't do that. The longer you get a sense as to what's happening, and I pick 5 minutes because in almost all of the cases that we looked at, that was about the time scale at which these large waves were arriving. Now, of course, if it's the first one that's arriving and the beach is totally dry, that's not going to help you. But the most important thing, the most important piece of advice that I want to leave you with is to have an exit plan. Time and time again in these videos where you see individuals being impacted, you see what we saw in one of the videos, folks running away, sometimes fast enough to get out of the way, if they're able-bodied enough to be that fast. But then they get nailed against something, be it rocks or be it a high dune, and there is no exit plan. There is no path through which they can escape, and the water just runs up their bodies. So when you find yourself on the beach, think about an exit plan. Think about positioning yourself in a place where you can get to high ground relatively easily without necessarily having to climb over something steep, for example. So that's the 3 things. Don't turn your back. Let's have a very healthy respect for what the water can do. Let's watch the beach and also the forecasts. The forecasts are getting more and more accurate by the day, and I am actually really proud to have done work that features in those forecasts. And please, every time you sit down or decide to take a seat at the beach, let's have an exit plan. Thank you.
I just learned a lot.
Oh,
Thank
good.
you.
Thank you.
So we're going to open up to questions. We're going to start with Coast Online. Roseanne, any questions? Okay, so for folks online, if you have any questions for Tuba, go ahead and put them into the chat. How about folks in the room? Oh, there we go. Okay, I'm going to start way back here because I see Bob's hand, and I got to go to Bob first.
Oh, I have to stay in the box. I forgot.
Thank you. Thank you, Tuba. That was really interesting and educational, and it's nice to see how those sorts of analyses can be made. I know they're very different, but can you tell us a little bit of how rogue waves are generated and what maybe some of those differences are?
Yes, thank you for asking that question. And I get that a lot. Our sneaker waves related to rogue waves. So rogue waves, of course, are waves that happen in the open ocean that are extremely large, and there is a formal definition that basically says, more than so many % larger than the average wave. And it was in the 1980s when the idea of rogue waves first came about. And at first, I think we just all thought that it was sort of like, stories. The wave was so big, and every time you tell the story, it gets bigger and bigger, right? Like the fish we catch. But as it turns out, the first rogue wave was recorded in the 1980s by an oil drilling platform. And there it was, this unusually large wave in the middle of a relatively calm sea. And there is an entire field of researchers who then worked on understanding these, because these can, overtop ships. They're a real danger to in navigational situations. But of course, rogue waves, if a rogue wave was to come to shore, it would just break way offshore. And by the time it came to shore, you couldn't really tell apart that it had been a rogue wave in the deep ocean. So rogue waves and sneaker waves are not the same thing. They're a statistical outlier in terms of what is happening on that particular day. So all of the methods that people use to study rogue waves, we have been able to put in play here. The science, the math is similar, but they're not connected. A rogue wave doesn't cause a sneaker wave. And I know that's not what you asked, but just to put it out there.
All right. I think I got a question online. So go ahead, Roseanne.
How do you stay safe if hiking the Oregon Coast Trail paralleling the waves? Avoid January?
January. I like this question. Thank you for infusing some humor into it. I will say January, November, December, January, February are probably the months where, statistically speaking, these occur most often. Strangely enough, those dates, January 16th and 18th, I brace myself every year, year after year in January, I get calls from, the press after a particular incident. So one of the important things here, if you are really, if you're going up and down the coast, is to just stay on high ground, right? As long as you are on high ground, way above, and, certainly a lot of the trails that you would be hiking on the Oregon coast would qualify. But if not, if you are in, sort of the general beach zone, and you're in the beach zone, usually, if you're in a vegetated area, it's highly unlikely that you'll be affected by this. But if you are somewhere where there's actively logs present, sandy beach, you're looking at an active situation where run-up must have gotten there, right? Because the logs wouldn't be there otherwise. So those are some of your clues that you're in an active nearshore swash zone area. So, but back to keeping yourself safe, certainly the National Weather Service forecasts have gotten more and more detailed. So, making sure that you follow them on social media and keeping track. And then in general, just having a path to high ground, not that different from the advice that we would give for a regular tsunami, right? Just charting your path and making sure that you do the thinking ahead of time so that when you have to react, you can do so quickly.
All right. Question in the room.
Thanks for a really, really interesting talk. I just noticed on like the one of the latter slides, I think the sneaker wave index, it seemed like you had really strong correlations for pretty much all sites except for maybe Crescent City. And so I was wondering if there's some way that like bottom morphology or the shape of the coastline somehow really can affect the predictability or likelihood of sneaker waves.
Yes, yes. There is definitely influence of the offshore underwater topography on what happens. So another study that one of my graduate students carried out that I haven't showed you here was to look at sneaker wave probabilities up and down the Oregon coast. So one of the things we're finding, for example, is that they are less likely in the middle of the state and occur more to the south and the north. And we think that that's got something to do with the fact that there's a bank out there, right, offshore of Newport. So interestingly, Crescent City too, right? So we haven't quite pieced those things together yet. So there is, right now, when the National Weather Service issues a warning, they issue a warning for the whole coastline. We haven't gotten yet to the point where we could be a little bit more specific, where we could say, this part of the Yachats area is more likely to experience sneaker waves today. That would be the next step. And in order to do that, you have to understand what's happening in the deeper area of that deeper area of the coast.
All right, Roseanne, go ahead.
Is there a time of year when the frequency of sneaker waves is generally higher?
Yes. So winter months, November, December, January, February, higher probabilities. Summer months, less so. And this has got to do something with the fact that during the winter months, you are more likely to have these distant storms that produce these swells that arrive. The National Weather Service folks sometimes call these the forerunners, meaning they are the longer waves associated with a far storm system that arrive first, right? So sometimes you can hear people talk about, oh, today looks like a forerunner day. Yes, so winter months, calm day, no wind, oftentimes sunny, long, beautiful swell coming in, beware.
All right, question in the room.
Thanks, Tuba. So for a couple of those examples you showed, there was an abrupt increase in the period of the waves kind of at the beginning of it. So what causes that?
That's exactly the clue. That's when the faraway swell is beginning to arrive. So before that, the waves are about 10 seconds, the usual kind of Oregon waves we know and love. And then that sharp increase happens because the swell is actually coming in like a front, right? And when the first waves associated with that front arrive, the buoy experiences the increase in the period, and they bring with them the bound waves that are now going to run up and down the beach every 5 minutes for a couple of hours.
All right, question online. Go ahead, Roseanne.
This is a comment we'd like you to talk about. I find the sneaker wave warning signs very misleading in showing very high waves, possibly rogue, instead of conveying low waves that keep coming.
Yes, that's such a really, really important comment. I thank you for that feedback. And you are absolutely right. I mean, I don't have one displayed here, but the sneaker wave signs look like the wave is going to break over the human or something like that. And that is not what these look like, which is also one of the reasons why I wanted to show you all these videos, right? They really just look like the wave, the water keeps coming. This is fantastic feedback that I will definitely take to my collaborators. So I appreciate that comment.
All right, we'll do a couple more and then we'll let you off the hook, but hang in there with us.
Thank you.
Thank you. I've lived here a long time and I've struggled every time that I go look at the ocean to count waves. I see the Coast Guards out there at Chicken Point occasionally just watching waves and counting and making some sort of a record of that. What are they looking at? Are they watching the green buoy out there go up and down, or are they actually counting the waves, or what are they looking at?
I don't know the answer to that. I don't know the answer to that. But they might be counting. Yeah. And, it's actually not that hard to determine what the period of the waves are just as a, person watching the ocean, especially from a high point. So, you can get a sense like what I do usually is if I'm at a high point looking down, I pick an object, I don't know, it could be a tree limb or something that can help me just focus my aperture. And then once the wave crest passes, I start counting 1001, 1002, 1000. I'm waiting for the next wave crest. So that's one way, even if you haven't had a chance to look at any forecasts, you can, if the waves you're seeing are 20 seconds plus, that's a day to be careful around. But I don't know how the Coast Guard operate when it comes to these things, to be honest with you. I have not interacted with them in that way. Oh, maybe.
Besides the monthly seasonality, is there any further correlation with lunar cycles within the month?
No, we find that oftentimes the events that the Coast Guard has, recorded are oftentimes associated with the situations with rising tides. But I believe my hypothesis is that that has more to do with human behavior than it has to do with physics. And that's because when the tide is rising, it makes it even harder to judge how far the run up is going to come, because the entire water level is increasing on top of that too. But when we look at the statistics, we see no correlation between tides and these occurrences. Good question.
We're going to wrap up with our last question, Roseanne. Go ahead.
I love it when I get a question that is actually a question that I've asked myself and then dug into the data to answer. That always makes me feel good.
Okay, can we expect more favorable conditions for sneaker waves with the changing trends in climate?
Oh, this is an interesting question too. So should we be having more sneaker waves or less sneaker waves in the future, depending on, I don't know the answer to that question. So we would have to backtrack and essentially analyze how much or less likely it is for us to get these, Goldilocks conditions where we have big swell coming in, also no sea. That's a complicated question that I have not asked myself, but maybe it can be the topic of my next proposal. So thank you for that idea.
That's great. Thank you so very much for sharing with us
Thank
and
you for
sharing your
being
message.
here.
I appreciate it.
Thank you.
To everybody in the room, thank you so much for being here. It sounds like it's still raining out there quite a bit, so drive safely home. And next time you're on the beach, count those waves coming in. And thanks, everyone. We'll see you next month. Thank you, Tuba.